Okay. So, Chapter 0, a review of basic algebra. So Section 0.1, sets of real numbers. So first off, a set is a well-defined collection of objects. So things like, say, the set of all states in the United States that begin with the letter M. That's a well-defined collection of objects. So X, being a member of a set, is denoted by, suppose that X is a member of the set A, then we denote that by X and then this symbol here, which means is a member of the set A. The set that contains no members is called the empty set. So we denote the empty set by this symbol, or just by two brackets with nothing in the middle. So this is called the empty set or the null set. It's a set which contains no members. A subset. So the set A is a subset of the set B if every member, X, in A is also a member of B. So if X is a member of A, then X is a member of B. If that is true, then A is a subset of B. So every member of A is a member of B. So A is contained completely within B. Superset. Well, B is a superset of A if A is a subset of B. Equal. The set A is equal to set B if A is a subset of B and B is a subset of A. A proper subset. A is a proper subset of B if A is a subset of B and A is not equal to B. A proper superset. B is a superset, a proper superset of A if A is a proper subset of B. In other words, if B is a superset of A and B is not equal to A. The difference of two sets. A without B is a set of all X in A such that X is not a member of B. So it's everything that's in A but is not in B. So we take away any member of B from A. So it's A but take away B. B removed from A is just A take away B. The universe. So the universe is a collection of all possible sets. Please note that a universe might not be a set. So the reason for a universe is because there are several paradoxes that occur if you assume that the set of all sets is a set. Complement. So the complement of a set. Denoted by, well, several different ways. A with a superscript C, or A with a little dash, or A with a bar, or minus A, or this symbol here, which means the negation of A, or this symbol, which again means not A. So not A, or the universe without A. So the complement is just the set of all x's in the universe, such that x is not in the set A. And so if this is the universe here, and this is the set A, then everything outside of A is a complement of A. Ordered pair. So an ordered pair is, well, a set, but it's a set of two objects such that the order makes a difference. So the ordered pair AB is different than the ordered pair BA, unless A is equal to B, of course. And so we can think of the ordered pair AB as just being the set containing the set having the member A, along with the set having the members A and B. So if you do this, well, what you'll notice is that if you reverse A and B, then you'll get something that's different. So Cartesian product. The Cartesian product, denoted by this little X here, is the following. So the Cartesian product of the set A with the set B is just the set of all ordered pairs AB, where A is in the set A and B is in the set B. Examples of the Cartesian product. Well, the plane R2 is just the Cartesian product of R with itself. Also, the complex numbers is the Cartesian product of R with itself. And, well, I can even think of, along with some identifications, I can think of the rational numbers as being the Cartesian product of, let's say, the natural numbers and the integers. Union. So A union B, so union is denoted by this, is just a set of all x such that x is in A or x is in B. And so if this is a set A and this is a set B, then A union B is everything in either A or in B. Intersection. So A intersect B is the set of all x such that x is in A and x is in B. So x has to be in both A and B. And so if this is A and this is B, then A intersect B is the overlap of A and B. So it's the set of all objects which are in both A and in B. Let me give you some properties of sets. The commutative property. So union is commutative. So A union B is the same as B union A. Intersection is commutative. So A intersect B is the same as B intersect A. Union is associative. And so A union B union C is the same as A union B union C. Intersection is also associative. So A intersect B intersect C is the same as A intersect B intersect C. We also have the distributive property. And so intersection distributes over union. So A intersect B union C is the same as A intersect B union A intersect C. Similarly, union distributes over intersection. So A union B intersect C is the same as A union B intersect A union C. So these all look very similar to what you have seen with numbers. The idempotent properties. And so union is idempotent. So A union A is just A. Intersection is also idempotent. So A intersect A is just A. Some inverse properties. A union A complement is just the universe. Good. It's gone. A intersect its complement is just the empty set. The complement of the universe is the empty set. The complement of the empty set is the universe. The complement of the complement is the original set. The difference of A and B is just A intersect the complement of B. Some absorption properties. A intersect A union B is equal to A for any set B. Similarly, A union A intersect B is just A for any set B. Universal bounds. A union the universe is just the universe for any set A. A intersect the empty set is just the empty set for any set A. Some of the De Morgan laws. And so, A union B complement is just A complement intersect B complement. A intersect B complement is just A complement union B complement. Okay, so that's several properties of sets. Russell's paradox. And so Russell's paradox is the following. Define the set B as the set of all sets A such that the set A does not contain the set A. So notice the following. So why is it a paradox? So suppose B is not a member of B. Well, if B is not a member of B, then B here is in this set. So that's a contradiction, because you said that B wasn't a member of the set B. But if it was, then it's in this set. So now suppose that B is a member of B. So suppose that B here is a member of B, but if B is a member of B, then that says that B is not a member of B. So that's a contradiction also. So no matter what, this is a contradiction, is a false statement. And so that's a paradox. You can't have that both the statement and its opposite statement are false. So this was resolved by having the universal set. So the way to resolve this is to say, well, the set of all sets is not a set, not necessarily a set. It's a universe. So if you do that, then you'll get out of it, then this won't be a contradiction. Okay. The Banach-Tarski paradox, which says that if you assume the axiom of choice is true, that's one of the fundamentals of set theory, it turns out that then if you look at any sphere then you can subdivide it into a finite number of pieces, 3 pieces. You can translate them, move them to a different place, and but do it in a rigid motion. So only move it. Don't like compress it or expand it. Just move it. Each of these 3 sets into different parts of space. If you do that, then you can actually double the size of your sphere. So what this says is that if you assume the axiom of choice is true, then you can subdivide a golf ball into a few pieces and reconstruct it so it has the same volume as, let's say, the sun, just by moving it to the sun. So that, what is that? Why is that off? Hmm, hide, hide that. Okay, so don't know why that's there. That just sort of came up. Okay, so can't do that. Someone accidentally put that on there. Okay, so if you uh, assume the axiom of choice is true, then you get this paradox. But the axiom of choice is actually very useful. Um, that's the easiest way to construct real numbers, is to assume the axiom of choice, and the easiest way to, let's say, uh, show that, well, actually, it's the only way. If you assume the axiom of choice, then every vector space will have a basis. So there are a lot of good things about the axiom of choice. One of the bad things is obviously this contradiction. So most people just sort of say, well, we'll live with the axiom of choice and hope that in the future, eventually, we'll have a axiom of set theory that is good as the axiom of choice, but isn't the axiom of choice, and it doesn't have these horrible sort of paradoxes. Okay, number sets. So now that we have looked at sets, let me define some nice sets. So the set of natural numbers. I'll denote the set of natural numbers by n, standing for, well, number. It's just a set 1, 2, 3, etc. Whole numbers. So we will denote the set of whole numbers by W for whole number. It's just 0, 1, 2, 3. So it's the natural numbers with the addition of the number 0. You can construct the whole numbers as follows. If you can define what's called a successor function. It's the next number. Uh, After 7 is the number 8. After 35 is the number 36. And so I can define the successor of the number n by n union the set containing the set n. And so you can define 0 as the empty set. Define 1 as the successor of 0. Well, I know 0 is the empty set, so successor of the empty set, which by definition is the set containing the empty set. Because the empty set union anything is just that anything. Well, the empty set I said was 0. 2 is the successor of 1, but 1 was the set containing the empty set. And so it's the set containing the empty set union the set containing the set containing the empty set. And so it's just the set containing, well, the empty set and the set containing the empty set. So it's just the set containing 0 and 1. So by analogy, 3 must be 0, 1, 2, 4 must be the set 0, 1, 2, 3, etc. So you can define in this fashion the set of whole numbers by way of sets. Integers. We will denote the integers by the letter Z for the German word for number, Zahlen. And so these are, well, 0, 1, 2, 3, 4, and -1, -2, -3, -4, etc. So it consists of the positive integers, 0, and the negative integers. The rational numbers. Yes, yes, I can hear you. 0 0.1. So this is the section 0.1. It's the very, very first section in the book. Oh, no, 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 no. So if you haven't read the latest email. So if you read the latest email, um, there's been changes. So this will be extra credit for section 0.1 and other sections throughout. It's because for the next 2 weeks, we won't meet. So I'm going to go through all the previous sections all the way up to the end. Okay? No, no, it'll be every day. Uh, if you look at all those CCC confers, those will give you extra credit. Yeah, and I'll go through all the sections. Okay? Just 0.1. That's it. Okay? Okay, rational numbers. Sure. So rational numbers are denoted by the letter Q for the Latin word for number. It's just a set of all numbers of the form P over Q, where P is an integer and Q is a natural number. Basically, I just don't want to divide by 0. So it's numbers whose decimal representation terminate with some finite repeating uh, decimal. So examples would be 1.432323232, etc., which we usually denote by 1.4 with a 32 with a bar over it, or -4/3, or 8, which I can write as 8 over 1, or 9, which I can write as 3 over 1, etc. So those are examples of rational numbers. Irrational numbers, denoted by the letter Q with a little dash, meaning they're not rational. So not rational, the complement of the rational numbers. So these are numbers whose decimal representation does not terminate with a fixed repeating decimal. So examples of irrational numbers are, well, this symbol here denotes the symbol for pi, which is the ratio of the circumference of a circle to its diameter. The square root of 2 is irrational. You cannot write 2 as a ratio of two integers. As a matter of fact, the square root of any non-perfect square will be irrational, in particular the square root of 7. And in general, the root of any non-perfect power is going to be irrational. So the cube root of 5 is irrational because 5 is not a perfect cube. Later on in the course, we'll introduce a number, e, and that turns out that that number is also irrational. Real numbers, denoted by the letter R, obviously standing for real numbers. These are numbers that have a decimal representation. So examples of things that are not real. Well, 0 divided by 0 is undefined. You do not want to divide by 0. It's a indeterminate because, well, later on you'll find that not only is it undefined, but if you try to define it, it'll have a multiple amount of differing values. So it has more than one value. So it's indeterminate. Next, 5 over 0. Again, that's undefined. You don't want to divide by 0. you could actually define this eventually as the compactification of the real numbers. And so you can think of this as just being the north pole of a circle, and really 5 over 0 you can think of as being infinity. Let me try to get rid of this. Next, 0 to the power 0. That's undefined. If you notice, 0 squared is 0. 0 to any non-zero power will be 0. But 5 to the power 0 is 1. 20 to the power 0 is 1. So any non-zero base to the power 0 will be 1. So what's 0 to 0? Well, it's somewhere between 0 and 1. So again, this is undefined, and again, it's indeterminate. There's an infinite number of differing values that it could take if you try to define it. Next, the square root of a negative number, like the square root of -4, that's undefined today. Later on in the course, we'll be studying complex numbers. So it turns out to be a complex number, 2i. Okay. So I sort of introduced this 5 minutes ago. The axiom of choice. So this is the least upper bound principle. Every set of real numbers has a least upper bound. And so let me explain what I mean by least upper bound. Let A be a subset of the real numbers. Then U, a real number, is called an upper bound if every number A in the set big A is less than U, less than or equal to U. L, a member of R, the real numbers, is called a least upper bound for A if L is an upper bound for A and L is less than or equal to any upper bound of A. Let me give you some notation. And I'll do this as a left multiplication coset. Of course, right still is also true, but I'll write as left just because I do. So let A times B be the set of all A times B, where B is in the set B, where A is in set A, is a multiplicative group, and B is a subgroup of A. Let me do this for right additive coset. So A plus B is the set of all A plus B, where A is in the set A. So this is where B is in the set B, is an additive group, and A, the set A, is a subgroup of the set B. So with that notation, I can write certain sets. So some additional number sets. The even numbers are denoted by 2 times the natural numbers. There's just 2, 4, 6, 8, etc. So we can think of this as being, well, 2 times 1, 2, 3, etc. So just multiply each of these numbers by 2. And that gives you the even numbers. Next, the odd numbers. 1, 3, 5, etc. is just twice the whole numbers plus 1, or twice the natural numbers minus 1. So we can think of this as you take these even numbers and subtract 1 from each of them. So 2 minus 1, 1, 4 minus 1, 3, 6 minus 1, 5. So that's one way of thinking of the odd numbers. The irrational numbers is just the real numbers take away the rational numbers. The real numbers can be thought of as the rational numbers union the irrational numbers. Note that the rational numbers intersect the irrational numbers is the empty set. So the real numbers is a direct sum of the rational numbers and the irrational numbers. There's a relationship between these number sets. The natural numbers is a subset of the whole numbers, which is a subset of the integers, which is a subset of the rational numbers, which is a subset of the real numbers. The positive integers are just the natural numbers. So they're just the integers that are positive, denoted with a plus as a subscript, or with a greater than symbol as a subscript. It's just the natural numbers. The integers which are greater than or equal to 0 are just the whole numbers. The integers with a subscript of less than are the negative natural numbers, the negative integers. A composite number. N, being a natural number that's not equal to 1, is composite if it can be written as the product of two numbers, neither of which is 1. Of two natural numbers, neither of which is 1. A prime number is a natural number which is not 1, that is not composite. Interval notation. So before I give you interval notation, let's just assume A is less than B. It'll make it notation easier. So let's look at the closed intervals, and let's start with the finite closed intervals. And so the closed interval A to B, denoted by having these square brackets, is just a set of all x, such that x is between A and B, and includes everything between A and B, and it also includes the endpoints A and B. In addition to that, we have the singleton A, which is just the set containing just the number A. So it's just that number A. Let's look at the infinite closed sets. And so the set of all numbers less than or equal to A is denoted by, well, I never include infinity, and so I have an open parentheses, negative infinity, comma A with a closed bracket. So I include the number A, but I never include infinity. The closed interval, which includes both A and every number greater than A. So it's a set of all x greater than or equal to A. It's just closed bracket A, comma, infinity, and again, you can include infinity, so it's an open parentheses. The open intervals. So first, let's look at the finite open intervals. The set of all the set of all numbers between A and B, it includes neither A nor B. So the set of all x between A and B, denoted by parentheses A, comma B. The infinite open interval. The set of all numbers less than A, so the set of all x less than A, is denoted by open parentheses negative infinity to A, comma A. The open interval, which includes all numbers greater than A, the set of all x greater than A, is just the denoted by parentheses a comma infinity in parentheses. The half open, half closed intervals, say the interval that contains all numbers between a and b. It includes b, but it does not include a. So it's a set of all x between a and b. It includes b, but not a. So it's the open parentheses a comma b close parentheses or close brackets. The other half open, half closed interval, the set of all numbers between a and b, includes a but not b. So the set of all x between a and b, it includes a but not b. So I have a closed bracket a comma b close parentheses, open parentheses. The clopin intervals, intervals that are both open and closed. And so the set of all numbers from negative infinity to positive infinity. So every real number is a clopin interval, and the set that contains nothing, the empty set, is a clopin interval. Absolute value. So the absolute value, denoted by these two lines, is the absolute value of x is the distance between x and 0. It is the magnitude of x. If x is a real number, it's the square root of x squared. It is x if x is non-negative, and it's negative x if x is negative. If x is negative, you want to change its sign so that you can make it positive. We define the distance between a and b as b minus a in absolute value. So let's do some problems. On page 13, determine whether each statement is true or false. So, problem number 26. Is the set of rational numbers a subset of the real numbers? Is every rational number real? Well, sure. And so this is a true statement. If you have a fraction, it is certainly it certainly has a decimal representation. Next, is the set R, the set of all real numbers, a subset of the set Z, the set of integers? So is every real number an integer? No. So this is false. Not every real number is an integer. So let's say pi is a real number, but it's not an integer. Saying the square root of 2 is a real number, but it's not an integer. So there are many, it's not I said a rational number. It's not a rational number either. It's not a integer. So you could pick 1/3. 1/3 is a real number, but it's not a integer. And so very few numbers are just integers. Okay, let's do problem number 58. Write each inequality in interval notation and graph the interval. Okay, so let me graph this interval. So I have, notice that this is in standard form. By that I mean an inequality is in standard form if the variable is on the left-hand side, no variable on the right-hand side, and you have some inequality. So it's a variable inequality symbol. Well, I guess I need more room here. and then followed by, say, a number or something. So if you have something in standard form, such as the above, then we can easily draw this. Note that if it's in standard form, then this arrow here, let's make it a little bit bigger here, points in the same direction as this arrow. So this arrow points in the same direction. Okay, let's write this in interval notation. I guess I got to move this down, this next problem. So this is the interval. Well, it starts out here. Well, there's it doesn't start anything. So you can go all the way down to negative infinity to 4. What in the world? Okay. 1 second. Come on. Sorry about that. Oh, here it is. To the number 4. It does not include the endpoint 4, so I do not include it. And that is your answer in interval notation. Okay, so write each pair of inequalities as the intersection of two intervals and graph the result. Okay, so let's do that. So I have here the set x, maybe I'll do it in red, greater than or equal to negative 3. So it's greater than or equal to, okay, 1 second. Obviously it doesn't like that. So it's greater than or equal to negative 3. And x is less than 6. So here I have x is less than 6. So I do not include 6, but I include everything less than 6. Okay. Oops. So this is 6. So now let's do the this is an and. So let's do the and of this. So this is going to be the overlap between these. So it's going to include everything between negative 3 and 6. It will include negative 3, but it will not include 6 because 6 is not included. But it will include everything else. So that's the intersection between these two. Okay, so, oops. So this will be, well, the intersection between these. So it's the half open, half closed interval. It is the intersection between these two sets. And it's just equal to the half open, half closed interval. Okay. So I want to write each expression without using absolute value symbols. Well, pi minus 5 is less than 0. So to write it without an absolute value symbol, I have to negate it, bring in the minus inside the parentheses. I have that this is a negative pi plus 5, and so this is 5 minus pi. And so I've rewritten this as a quantity without absolute value symbols. Notice that 5 minus pi is positive, and you want that the absolute value is non-negative. Let me do problem number 97. Oh, then that'll be it. Find the distance between the pair of points on the number line. So I want to find the distance between 3 and 8. If we remember, the distance between A and B is just the absolute value of their difference. Well, 8 minus 3 is 5, and the absolute value of 5 is 5. And so that's the distance between these two numbers. And that's it for today. And so you can, here, I'll stop the recording here. You may submit